Okay, it's time to tackle the largest circuit we've seen so far in this class, and by far the most detailed analysis. We're asked here to find the voltages V1 and V2. So here's V1 above the 6 ohm resistor, V2 is right here above the 3 ohms and the 2 ohms. We're also asked to find I sub 1, which is right here, I sub 2, I sub 3, okay, I guess those are the only ones we're required to find, but then there's I sub A, I sub B, and I sub C and I sub D, which are also labeled for our convenience. If those weren't already labeled, we would probably end up having to label them, but we're not required to find those. We're only asked to find V1, V2, I1, I2, and I3. So if we happen to be able to skip one of the other variables, then that's just fine. Well, the very first thing that I'm going to notice is that before I do any other work, I can calculate the current I1. I only have to find 5 things, and I can find one of them just by glancing at the circuit, because the 12-volt source is in parallel with the 4 ohm resistor. That means that the voltage across the 4 ohm resistor is 12 volts. And if I know the resistance, and if I know the voltage, Ohm's law will allow me to calculate the current. So the very first thing that we're going to do here is see that I1 is 12 volts divided by 4 ohms, which is 3 amps. Now that serves 2 purposes. First of all, great. We've answered one of the 5 things we were asked to find, but I1 will also be a valuable thing that we're going to need to find later on. Now that we've got that out of the way, I see that the 3 ohm and the 2 ohm resistors are in parallel, and I see that the 6 ohm and the 7 ohm resistors are in parallel. I'm going to go ahead and combine those together. So the product of 6 divided by the sum of 5, that's going to be 1.2. Over here, the product of 42 divided by 13, and if you have 42 divided by 13 memorized, it's 3 point something. I don't have it memorized. It is 3.23. So there's 3.23, and down here's the 1.2 ohms. Now, notice that when we combined those together, we lost a couple of the currents. We lost I2 and I3. They're no longer available in the circuit because they were in one of the 2 resistors that were just combined. Now, another thing that I did, if I'm going to flash back up to figure 3, and I'm going to be going back and forth amongst all these figures here quite a lot, but notice that V1, because it's just labeled on a particular node, that's obviously relative to ground. Now, ground is, as traditional, is drawn across the bottom of the circuit here. So what that means is that I want to know the voltage V1 relative to ground. And all I have to do is really drag my finger or my cursor back and forth there, and it becomes apparent that I'm looking for the voltage across the 6 ohm resistor. And in the same way, V2 relative to ground, well, that is across the combination of the 3 and the 2 ohm resistors. So what I've done in figure 4 is I went ahead and explicitly labeled that. V1 is across this resistor, and it's now the parallel combination of 2 resistors, and V2 is across the parallel combination of 2 resistors as well. That's a good practice so that you can be sure to see exactly what voltage and exactly across what resistor you're looking to combine. Now I see here that there are 2 resistors in series, the 5 and the 1.2, and another pair of resistors in series, the 8 and the 3.23. I'm going to go ahead and combine those. And so when I do that, I end up with this circuit right here. 8 and 3.23 became 11.23, 5 and 1.2 became 6.2. Unfortunately, I lost the labels for V1 and V2. They can't be shown on the circuit diagram anymore because they were combined with resistors being combined in series. So I'm going to have to go back to figure 4 eventually, but the circuit's getting simpler. I still have I sub A, I sub B, I sub C, I sub D, and I sub 1. All of those are still on the circuit diagram, so that's good news. I also see that I have 3 resistors in parallel. So I can combine those 3 resistors in parallel. I could combine 2 of them and then combine that one with the 3rd, but I also have just a single equation here that allows me to say that the equivalent resistance is 1 over the sum of the reciprocals of the 3 resistances. So I invert each resistance, add them, and then invert the sum. And I get 1.998 ohms. So ultimately, that entire big circuit diagram that we started with in figure 3 is going to be reduced down to this circuit diagram, which is just a single resistor. Now notice that all of the other currents, I1, IB, IA, IC, all of them went away. The only one that remains is I sub D. But I sub D is enough. If I look at this circuit diagram, I can now easily find I sub D. It's going to be 12 volts divided by 1.99 ohms. So I'm going to calculate I sub D, and it works out to be 6.00 amps, just 6 amps. Now I have to go backwards. I'm going to go back up to figure 5 now. It's because I sub D is in figure 5, and I know the value of I sub D. And I sub D Oh, but I also know the value of I sub 1. Remember, we calculated that as 3 amps at the beginning of the problem? So I could do Kirchhoff's current law at this node right here above the 4 ohm resistor, and I could calculate I sub B. I know I sub D, I know I sub 1. If you know all the currents at a node except for 1, you can calculate the 1 current that's missing. So I'm going to calculate I sub B by Kirchhoff's current law. You can see here I wrote Kirchhoff's current law the first time with the sum of the currents entering equals the sum of the currents leaving. Then I rearranged it so that the unknown variable was on one side. And 6 amps minus 3 amps gives me 3 amps. Okay, I sub B, not one of the required variables, but it's very helpful in solving the rest of the circuit. I'm going to use current division now. So I'm going to go back up to figure 5. I now know I sub B flowing into this node right here. I have one current division that needs to be done, and that is to divide the current going down through the 6.2 ohms and going down through the 11.23 ohms. They have to add up to 3 amps because this is the total current, 3 amps, that's flowing into that node. Part of it's going to flow down here, part of it's going to flow down here. More of it will go through the 6.2 ohm resistor because that's the path of least resistance. So when I calculate I sub A and I sub C, I should find that they add up to 3 amps and that I sub A should be larger than I sub C. Here you can see that I calculate them. They do add up to 3 amps, and I sub A is larger than I sub C. So I actually have now found I sub 1, I sub A, I sub B, I sub C, and I sub D. And now I'm going to go back up one step earlier. So I'm going to go back up one figure earlier to this figure right here, figure 4. So I now know I sub A. I know the current that's flowing down here, and I know the resistance, so I can calculate V2. And over here, I know I sub C. I know the current flowing down, and I know the resistance, so I can calculate V1. Those are 2 of the 5 quantities that I was required to find. So I can now multiply those and find out what those quantities are. So you can see here that I have V sub 1 is I sub C times the resistance, 1.07 amps times 1.2 ohms, gives me 1.284 volts. V sub 2 similarly turns out to be 2.316 volts. Now finally, we're going to go all the way back up to the original circuit diagram. And the original circuit diagram had a couple more current divisions that need to be done. You can see here that I have I sub A is flowing downward, and it needs to be split up into a part that goes into the 3 ohms, but the part that we care about is the part that's going through the 2 ohms. That will allow me to calculate I sub 2. Similarly, I sub C is flowing to the right, and I need to find what fraction of it is going to go down through the 6 ohm resistor. Just a couple of quick applications of Kirchhoff's current division is going to allow us to solve for those 2 quantities. So you can see here that we have I sub 2 is developed from I sub A by current division, and then I sub 3 is developed from I sub C by current division. And it kind of helps if you can look at the circuit diagram and think about how you would do the current division. But here you can find the final quantity for I sub 2 and the final quantity for I sub 3, and we've now solved the entire problem. Pretty much from all of the currents and the voltages that we've already found, it would be really easy to find any other currents and voltages in the circuit. It's like once you've done the hard work of doing the simplification and part of the re-expansion, the rest of the problem pretty much falls into place. Now, you get the opportunity to do simplification re-expansion problem 3. This example will take you some time, but work through it steadily. And once you've done your solution, go watch the video to see if you got the same answer that I did.